Hi, this video describes the operations of the adjacency list data structure for graphs. This builds directly on the previous video on the overview of the adjacency list, so make sure you've watched and digested that video before tackling this one. Let's do a quick recap of the operations that we need to define. There's a create operation where you give it n and it creates a new directed graph that has n vertices but no edges. We can get the count of the vertices and edges. There's a hasEdge function, which tells us whether there is an edge or not between two vertices. We can add an edge between two vertices, remove an edge between two vertices, and then outEdges is given a vertex, and it gives us a vector containing all of the destinations of outgoing vertices from that I. And inEdges is the opposite, given vertex j. InEdges gives us a vector of all of the incoming vertices into j. So first, let's look at the data members and the constructors and accessors. Just like the adjacency matrix, we have an int for n and m, the number of vertices and edges. And the main event is this vector of singly linked lists of ints called adj. This is where all of the edges are stored. And the idea is that adj of I is the list of all outgoing edges starting at I. So the constructor is given n, the number of vertices, and it initializes n accordingly. M, the edges are 0, and adj uses the fill constructor again. This says that that vector should have n elements, so that creates n empty linked lists. And creating a linked list is constant time, so this constructor takes big O of n time. Constant time to initialize n and m, and big O of n time to set up these n empty linked lists. The vertex count and edge count accessors are single line return statements. Those are constant time each. HasEdge follows this definition directly. Remember, the invariant is that adj of I is the list of the outgoing edges of I. So to determine if there's an edge from I to j, what we can do is look up adj of I and see if j is anywhere in that list. And if it is, the answer is true. And if j is not in that list, then the answer is false. So we've got error checks on the indices. We check I and j to be valid indexes, throw an exception if they're not, pretty standard stuff. And then we have this loop that goes for every e in adjacent of I. So we're looking at every vertex that has an outgoing edge from I to somewhere else. If j is in that list, we return true. So for every e in edge of I, if e is equal to j, return true. We can stop the search and say, yes, there is an edge there. And then after the loop, if we get through all of those vertex numbers and we never found a match, we return false to say there is no such edge. So this takes big O of the degree of I time. This is where this degree of I thing comes into play. This loop clearly repeats once for every element of this list, so we need to know the length of that list, and it spends constant time on each iteration. So degree of I is the length of adj of I, so this operation takes big O of degree of I time. Adding an edge is simpler actually. We've got the error checks on I and j, and then we just add to the front of that linked list. So adj of I is the list of all of the outgoing edges of I. If we're creating an edge from I to j, then adj of I needs to include j. So we just do a of I, adj of I, dot add front j, and that's it. And this takes constant time. We're adding to the front of a singly linked list, and that takes constant time. Okay, remove edge is simple in principle. Adj of I is the list of outgoing edges of I. We're trying to remove an edge from I to j. So first we have the error check. If not has edge I to j, then there is not actually an edge there, and we throw an exception. So we dispense with that case first. If we get past the if, there is a j in this list that we need to remove. So basically we loop through, find it, and erase it. This is a lot like the hash table erase operation. Find the one element of this linked list and delete it. So here I'm doing kind of an iterator-based loop. Start at adj I begin, end at adj I end, and if the iterator value is equal to j, that's the match we need to erase, and we do the adj erase it. That's the singly linked list erase operation. And we might as well break the loop. We know that we're not going to find a second copy of j in there anywhere, so we just stop the loop because we know we're done. So this takes big O of, or hasEdge takes big O of degree of I. So we spent degree of I time on hasEdge already. This loop repeats big O of degree I times in the worst case. Erasing a node from a singly linked list is constant time when you have an iterator to the node that needs to be erased, so that erase operation is constant time. So altogether, this takes big O of degree of I time. Okay, outEdges. Now, this is what we were hoping to speed up. So let's see if that actually happened. what we're trying to do is compute all of the outgoing edges starting at vertex I. So we've got another one of these range checks to make sure I is a legal index. And basically what we want to do is go to edge of I, which is a singly linked list of outgoing edges of I, and make a copy of all of those elements, but the data type is specified to be a vector, so we just need to copy that linked list into a vector. So we create a vector of int called out, and for each j that's in edge of I, we just do out.addBackJ. So basically copy all of the ints out of edge I and put them into out, then return out. So this loop repeats big O of degree time, and the whole operation is big O of degree of I time. And this is what we were hoping for. We got a significant speed up over the adjacency matrix. Remember, the adjacency matrix would loop through n columns here and take big O of n time. N is the total of all vertices in the whole graph. Instead, out edges is only looping through the actual vertices that are outgoing from I, so it takes big O of degree of I time, which is much smaller. Usually only a handful of the vertices in the graph are outgoing from I. Finally, in edges, we don't have such a helpful speed up here. We defined edge of I to be the list of the outgoing edges of I, and that doesn't help with in edges. With in edges, we're trying to compute all of the incoming edges into J. Edge of I doesn't help, so we need to do kind of a brute force thing and scan the entire graph for any matching edge and make a list of those. So we've got an error check to begin with, and then I've got my vector of ints called in. And what we're going to do is loop through every vertex and go through that vertex's adjacency list and see if we find any edge in that list that goes from I to J. So, or goes just to J, yeah. So it's kind of a brute force thing. We have the outer loop going through every row or every element of the adjacency list. And then for each row, we loop through that whole list. And if we find a entry that equals J, we add I to our list of incoming edges. So this takes big O of m plus n time. It's linear in the total number of vertices and total number of edges because this nested loop here visits every vertex and it visits every edge. So big O of m plus n time, linear in both the number of vertices and the edges. So here's a summary of all the runtimes. We've analyzed both of these data structures. Adjacency matrix is on the left and adjacency list is on the right. So to summarize what was in this video, creating the adjacency list is linear time because of initializing all n empty linked lists. The vertex count and edge count accessors are constant time. Adding an edge is constant time because we're just adding to the front of a singly linked list. Remove edge, has edge, and out edges are all big O of degree of I because we jump to edge of I, which is a linked list of all of the outgoing edges from I, and then loop through that linked list. So those take big O of degree of I time. And then in edges is kind of the loser here. It's even slower. It's big O of n plus m time because we need to loop through every single vertex and every single edge and check it to see if that edge is incoming to J.